summary, I have on the slides, you will see that there is this blue box here at the top that sort of gives you an orientation along the chapters roughly, the different lectures, the name of the file. So it's in blue here, so you can sort of get a sense for where we are. Good. So a summary of the course. So you're going to be really brief and just sort of maybe conceptual. It's just really trying to prepare you for the exam. So the introduction, I'm not going to repeat all of that, but maybe now in hindsight, once you have listened to the whole course, you could maybe make more sense of some of the things I said in the introduction. I was talking then about cognition in the wild. I called it the fact that, daily life behavior here, like playing soccer, involves a lot of cognition, I then said. And you might have wondered then if that's really makes sense. But now maybe you understand, that, for instance, selecting an object for your attention and maybe for gaze, doing that by actively, orienting in the world, not just passively receiving input, but actively orienting in the world makes sense. You might see that working memory is actually required to do that. You don't have to visually search for the ball every time, right? You are able to predict where the ball is approximately or where your other player is and so on. So that now might make more sense. You have maybe better idea what these things even mean: working memory, attention, selection, and so on. And then, of course, action. We didn't really have that much action in the course. It's more in the summer semester where we talk about it. But decisions, selecting a particular action for a decision and maybe how sequences are generated. Didn't really talk about goal orientation, motor control much. That's something that, again, is done in the summer semester. Learning was only touched also very briefly. You can see there's a lot of room for further research. We do address some of those things. And background knowledge is a particularly interesting one, which we're also very interested in, but haven't really gotten so far really here in this lecture. That's the state of the art. And so the other main point of this observation that cognition manifests itself in daily life behavior in the wild was this idea that the properties that come from this sensory motor grounding of cognition are properties of all cognitive processes. So this idea that there would be graded states, meaning continuous state spaces, that time would be continuous, that you could intermittently or continuously link to sensory or motor processes, that therefore discrete events in time and categorical kind of behavior emerge. But the whole thing happens in closed loop, and that requirement, that implying that you need stable states and so on, that might make a lot of sense for you now, right? And so the underlying hypothesis is that all cognition is like that. It's not just some evolutionary old simple form of cognition, but there's even higher cognitions like that. And, we got in the course, we got two grounding language sequences of phrases and so on. Our research actually goes further than that. The mental mapping might have been the most cognitive we ever got. So we haven't really, but language is considered usually the pinnacle of cognition, that you can generate and make sense of nested phrases and that stuff that we're dealing with in this way. Okay, so this is not so important for the exam because it's more like conceptual, but I did want to come back to that because that's part of really what drives our research program. The Breitenberg lecture was about sort of an illustration of things to come. It was this idea that these 5 things, sensors, motors, the nervous system, the body, and an environment in which all this happens, are sufficient to understand behavior and also necessary to understand behavior. That exercise of where we did mental simulation illustrated that, especially the environment actually does play a role. It's a very low-level thing. So maybe conceptually important things from this lecture is this idea of rate code in the periphery, this relationship between something outside the nervous system, intensity, and something inside the nervous system, activation. And similar for the motors, where it's just the same kind of mapping, but in the reverse direction, where given a certain activation that comes in, you get a certain physical thing, a wheel motion here in this example. So rate code, because there's a one-to-one relationship between the thing outside the nervous system, here the intensity or the motor action, and the thing inside the nervous system, the activation. Right? That's the idea of rate code. It's rate because this kind of activation typically in the nervous system is the rate of spike events. So that's maybe a useful concept to understand that as contrasted to later space code or population code kind of ideas. And then we argued in that lecture that there was behavioral dynamics. This was one of those online lectures, so I didn't even discuss it much, but that the mental simulation led to a dynamical system where the turning rate of the vehicle was a function of the current heading, and there's an attractor here. And that was an example of attractor dynamics, but the variable here isn't a neural one, it's a physical one, the body in the world. And now after this course, I think you're very familiar with this idea that if you have a derivative here of this variable, and the turning rate is the derivative of this variable, then you have a dynamical system when that's this unique function here, and then the zero crossing with negative slope is an attractor, right? So in the rest of the course, we did this for neural variables where this was activation. This introduction was a behavior variable. In the summer semester, I teach much more extensively about such behavioral dynamics. Yeah, and then that was just an announcement then that we are going to go for neurodynamics then. Then I had this neurophysics, so here, interrupt me anytime, right? So if you have any nagging doubt that came up as you did the essay or as you revised, ask me questions. So I did this brief neurophysics tutorial, which essentially drew your attention to the properties of the individual neurons in the brain, the typical cortical neuron here that has some complex dendritic structure. Here's the soma, where the spikes form, and then it goes down through some complicated axon onto other neurons, and the connections are made where these boutons are, the synapses are. So these are incoming connections, and then there will be some outgoing connections. And then so it's a forward structure in the sense that input comes on the dendritic side in the form of synaptic transmission, and then spikes form at the soma and are traveling down the axon, and these spikes then generate postsynaptic potentials on the target neurons. And so somewhere near the soma, you will be seeing an overall membrane potential that's negative, then interrupted by spikes. Extracellular, when you put an electrode in the brain, you will be picking up these spikes as certain voltage events, and at the axon, you will be only seeing where the spikes traveling. And here in this sort of simple illustration of what you would observe if you were to stimulate intracellularly, you inject a particular current into the membrane, you would observe then a response to that injection that has a particular time course, sort of exponentially going down, exponentially going up. When a threshold is reached, there would be this spike, the self-excited single pulse of activity. And the mathematical description of this potential is actually this description, which leads to exponential kind of behavior with a timescale that is similar to the timescale we're using in most of our modeling. It's a bit faster. You see, this is 10 milliseconds from here to here. See, it's not quite 10. It's probably here more like 3 or 4 or 5 milliseconds. It depends on the kind of neuron. So it's a little bit faster than what we look at the population level. And when we use the same equation at the population level, we're essentially averaging across many different neurons in effect. And if you do that, actually, the staggering, the fact that they're temporally staggered means that the population envelope will evolve more slowly. You don't need to understand that. Just tell you that. And so this way the notion comes from of threshold behavior. A single neuron getting a larger input would lead to that. But of course, in actual neurons, the input comes from spikes that the dendritic tree collects. And if these inputs are temporally close enough to each other and they're enough, then you can reach threshold. And the typical idea is in cortex, you need about 10 incoming spikes that are within a time window of about 10 milliseconds in order to make an actual potential. And it's kind of interesting to know that cortical neurons typically have 10,000 synapses. And so among those, 10 need to be activated, which is 0.1%, right? It's a sense for the extraordinary flexibility, the very many different ways of how a neuron can fire in response to many, many different combinations of inputs, but they have this temporal constraint. So this was used primarily to motivate this idea here, to motivate that we're using this kind of dynamics to describe the state of neurons. And in the population picture, we essentially replace this spiking mechanism by a sigmoid, by saying if we look at many neurons, then we can say that the fact that some spiked and some didn't means that overall the population level signal has a nonlinear dependence on the activation level in that population. So when it's sufficiently high, the neuron, the population responds, projects, has effects on downstream neurons. When it is below a threshold, it doesn't. And the steepness of that essentially fixes the scale of the activation axis. So the activation that we're using in all neurodynamics isn't exactly the membrane potential, which would be always a negative number involved. It is a population level variable where the threshold has been arranged to be at 0. So we have a simple idea. Positive means it is doing something like spiking, passing it on, the activation on, and below 0, it doesn't. Yeah, and the distance from 0 sort of says how much input it would need to reach that threshold, right? That's the population level description. We didn't derive that. We just phenomenologically modeled that is we wrote down a dynamics like that now applies to this abstract activation concept. And so that's where these ideas came from, that activation is a stable state that would be at a negative level here below threshold by default. That will be the resting state without any inputs. It's a fixed point and attractor. That's a thing you should really understand. Now, this kind of figure here, I think you should be really familiar with U dot versus U. That's what we call the dynamics of the neuron, right? It's something you would be now really familiar with, and I expect everyone to know what's on the axis when you plot that, right? Understand. So I'll say something about that at the end. And so in this picture, so this explains exponential behaviors, and the time scale of the exponential behavior is this number here at the left, which if you divide by that would be the slope of this linear characteristic, right? So that's what I was just arguing, that slope is, that time scale is similar to the time scale of the neurophysics of individual neurons. It's just a little bit slower due to the staggering. It's kind of an amazing fact, right? Relatively slow. If you think, we often think of 10 milliseconds as a population level activation. It's not really very fast, right? If you think of computers, they have clocks where the time for an individual update is like 10 to the minus of 10 seconds, right? It's extraordinarily much faster. And so neurons are, in that sense, very slow, very sluggish, not very far from the time that it takes to activate the whole organism in a reaction time, right? Which would be maybe 200 milliseconds or so. So just 20 times this much, you can get the whole organism to do something meaningful, like direct your gaze at a target or press a button. So that's the special thing, how the nervous system works, very different from computers. And so in this picture, inputs are contributions to the rate of change added here. So you shift the characteristic up, and the attractor therefore shifts into the positive range so that the sigmoid will return something if you do that. And so the neuron time course is continuous even in response to abrupt shifts of input. So that's a low pass filtering property. But then we we'll jump into action, which would change that picture. So dynamics is as such really just smooth out any changes in the input. Well, with the positive inputs being excitatory, shifting the system closer to the threshold, and negative inputs being inhibitory. So very basic ideas. So this neurodynamics chapter was a large chapter, right? I'm talking about this here. This was a chapter that involved all of this, and then it also involved self-excitation, the simplest form of recurrency. Just checking if there's any chat question. No. So a simple self-excitation, which shows up here. So the idea, I have to get rid of this bar here. How can I do that? Hide the video. No, that's not what I wanted. hide the floating, yeah, this one. So here the activation itself feeds back. So the equation is in terms of U, and there's a U-dependent term here, and that will be self-excitation, and that's sort of the simplest circuit that leads to, you add the sigmoid here, so the minus U, and if you add that sigmoid to the minus U, that shift here from the minus U, that is the sigmoid, right? And that leads to this kind of nonlinear characteristic, and that has this property that it can lead to bifurcations. That is, if you shift it through, there are phases where there's only one attractor, the off attractor here, negative activation. You shift it up, there can be another on attractor here on the right, and in the middle there is a repeller that separates it to two regimes. And if you shift it further, then there's again only one attractor, but not the on attractor here on the right, right? That's this famous detection instability. That is, if you shifted up the point where the subthreshold attractor disappears, that's called the detection instability. When you go down in the reverse, the point where the activated state disappears, that's the reverse detection instability. And whether or not that reverse detection instability occurs as a function of external input determines whether you have working memory or not. For a single neuron, that's not so obvious because it's sort of arbitrary to say what is input and what is age and so on. But in the field, that makes a lot of sense. So this is a very critical kind of slide. And I think understanding this here is a really good thing to understand. It's actually very good for many purposes. This is also how flip-flops work in the computer. It's a very general principle, bistable elements. So how to transform something continuous into something categorical in a way, even though the states still may shift in activation, but you could say the states here on the right are categorically different from the states here on the left. And they're separated by an actual boundary, by some jump. In fact, if you I cut that slide. If you, the hysteresis, remember the hysteresis would separate these two branches. So that's a very good slide. I always ask questions about this one. Okay. The other aspect was that, if you have two neurons, you couple them excitatorily, then the same thing happens. That's really the population picture of the same self-excitation. But if you couple them inhibitorially, so that here, the second neuron shows up in the equation for the first, and the first in the equation for the second, and it's a negative coupling, then that leads to selection, to competition. One neuron being activated, it would suppress the other neuron and vice versa. That was discussed in one of the video lectures. And this closed dot is sometimes used to indicate such inhibitory connections. And I didn't use these vector fields other than in that example. So if one neuron versus another neuron without input, it has this off attractor at negative levels, resting levels. And then if you turn an input on for both neurons here asymmetrical, there's more for the neuron 1 than for neuron 2. You have these on attractors here, but they're not both in this regime. They're not both on, only one, either U1 or U2 are on. And that's due to that inhibitory coupling. And that leads here to bistability, that is, you're going to select one or the other neuron. So for instance, if you're initially sitting here in the attractor, the no stimulus attractor, you turn on this vector field, then you will be more likely going to this attractor than to the other one, right? So you can bias the selection. This is sometimes called biased competition, is the sort of fundamental way of how decisions are made in nervous systems. So unlike the neural networks that you hear about in machine learning classes, where you're reading out the winner, right? You're just saying which neuron is most activated, and I'm saying that is the winner. It's an outside algorithm. In actual autonomous neural networks, it's through these sort of mechanisms that the system itself makes the decision and then really goes to a macroscopic state, usually will be a population state, where only one of the possible choices has above threshold activation that can affect downstream neural processing or motor behavior, and the other one doesn't. Right? The neuron number 2 here is below threshold, has a negative number, right? If you go to this one. That's selection. And then the step was to do that in fields, right? And so in the field would be, say, I have continuously many neurons like that. I can think of those neurons as being arranged along some axis, some dimension, with the idea that if you're close in that dimension, then you're in the self-excitatory or mutual, locally excitatory regime. If you're far enough, you have this form of inhibition. And we would then think about where these dimensions come from. And if you take it for granted for a moment, then I'm just going to say then that led to this idea of a field. That is, the field has the same mathematical form, and the locations that are close, where this is a small argument, would have a positive W, so it will be somewhere here, and where they're far, they have a negative W. This being negative, and that would be competing with each other. So that's how you get these two regions, right? The far and the close from one single equation, and the sum or integral over these x combines all these contributions, right? That's the math. And you can see that this kind of math works well when you have spaces x along which you have this regular pattern of activation. And then we were arguing that these spaces might arise from properties of the sensory surface and similar of the motor surface. So you have some implicit dimensions on the sensory surface. On simplest, let's say this is really a sensory surface, like the retinal surface, the position on the retina, on the skin, on the cochlea, and so on. And then you make a mapping onto some other dimensions. So that could be just a mapping of retinal space onto some, for instance, polar coordinates kind of visual space. Or it could be feature mappings, that these transforms here abstract orientation features, movement features, textures, really just spatial frequency features, and so on. Similar in the auditory domain could be, the sound frequency, which is called pitch, or it could be something about movement in sound is sometimes called performance, where you see some of the pitch changing. It's like the auditory equivalent to movement. These sorts of feature extractions can be arranged by forward connectivities that then go onto some other continuous space. And that would be one way of how these dimensions could come about. So for instance, if you have visual motion, then you could hypothesize that any particular object that moves in a particular direction would be one localized activation in this feature space that is spanned by movement direction and, for instance, horizontal position. And analogously, in the motor system, you could have some continuous representation that ultimately projects onto the motor surfaces and leads to some projection there. It's funny that the slide doesn't really fit here on this. Not sure why that is the case. Something wrong about this slide. So projects out there, and I didn't really explain that as well. And it's actually more complicated in the nervous system because we have these funny things that are called muscles, and they're special in that they only pull and don't push, and we have to have pairs of opposing muscles. It's a bit more complicated. And the idea would always be that in the motor domain, you really have a behavioral dynamics, not just that the muscle makes force, but that it is a mechanical system that has state, and therefore ultimately will have stable states if you do this right. And so there's a whole issue of how it's actually done that is discussed again more in the motor summer semester. But it's in principle analogous. So if you think of planning an action, for instance, that has a movement, let's say, directed to an object in a particular direction with a certain distance that leads to the movement amplitude, you could think of that movement being represented parametrically as an activation peak that's localized again in that space of movement parameters, which would span all the possible movements. And we're doing very concrete work to validate these kind of ideas. So that's the notion of fields. And then in the fields, we have these instabilities, the detection and selection, illustrated here in this one-dimensional simulation. And this repeats what I just said before, right? The peaks are then the attractor states. Here, working memory makes a little bit more sense because you could say, well, localized inputs are really the external inputs, and anything constant across the field is a different kind of thing. It's called resting level or sometimes boost. And we went through all these instabilities, right? And you have the online simulator to play with that. So that's also something. I mean, to understand the field here, the logic of that, to understand, for instance, to to understand what these patterns look like compared to input patterns, resting level, and these things. That will be really useful for you to know. And I actually encourage you to go to the online simulator on the dynamicfieldtheory.org page and do a simulation like that and really look at the field. You see here, for instance, the selection, one of the peak wins. You see the inhibition, everything going down. That's the inhibition from that peak. The resting level is the green thing here, right? This is the resting level. That's the localized input. To really understand that, I think that will be a good thing for you to understand and to connect it to this and to see what's happening. When does this term start to contribute? For instance, right now, maybe not now. It starts here and so on. And on that online simulator, you have very nice illustration because you can see the sigmoid here and so on. There is the one directly on the web page, and then there's the one that you can get by taking one of those drop-down menus. You'll find that. Yeah, so it will be good for you to understand that. The detection stability, the reverse one, the difference between a subthreshold versus a peak suprathreshold solution, what selection means. So this is detection, right? Going from this to this, that's reverse detection. Understanding selection, knowing what working memory means, and maybe the boost-driven detection stability is like the most fancy one. Okay. And so we had a whole lecture on aspects of detection instability, which really stabilizes decisions, right? You're fluctuating around a stable state. So you're not, if you say that, for downstream action, there's the slide I was looking for. Downstream action is going above to positive levels of activation, then you can see that you're not going to fluctuate around that. You're fluctuating around a stable state. So these fluctuations don't have behavioral consequences. While in the threshold piercing picture, you would really make a difference between being just below zero and just above zero, and that being the decision criterion. And then, a signal that fluctuates around that would actually cause unstable behavior. This is actually how the white noise, random walk model, sometimes called the diffusion model, works. The cognitive science students, a few who listened to my other lecture, saw this model. This would be the diffusion model of decision making. You see, it doesn't actually deal with the stabilization of decisions, so it's not really compatible with embodiment. And maybe that adds a little bit of understanding to that cognitive science lecture. Yeah, so stabilization of detection, that's what I meant earlier. There is a finite distance between the branch that is below threshold and the branch that's above threshold. This is this distance, which can show up as a form of hysteresis if you vary input continuously in time. It also leads to this emergence of the discrete moments in time. The very last lecture I did really showed how we're using these instabilities to create sequences autonomously. And that's really a very cool use of this notion. So it's very critical to DFT that works. Good, so that's the detection module. Selection, now is an illustration of just threshold piercing analogous to detection. You can also think of threshold piercing in selection, where, if you're always just looking for the maximum, then sometimes it will be on the left, sometimes it will be on the right. But through this induction, you're amplifying the decision and making that a macroscopic distance and stabilizing the selection decision, right? And we discussed, the large literature on reaction time, how to make sense of that. And in that literature, the distance between the go signal, the imperative signal that tells you what to do, and the task set that tells you what would have been possible outcomes is really the main determinant of that. That determines how easy the competition is. Yeah, I'm not going to go into a lot of detail, just mentioning the metric effect, a somewhat surprising effect where similar choices can be faster sometimes than dissimilar choices, just because they profit from the task set from mutual excitation. But you still need the stimulus that tells them apart. So you still need to engage selection somehow. Yeah, that's not so important. I did have this little excursion into learning, the memory trace being the major one. The memory trace is a somewhat abstract concept. We don't know exactly what its neural foundation is. There is empirical evidence for something like that, but no real consensus on how it's done mechanistically. So it's simpler than Hebbian learning in that it's only sensitive to whether there has been suprathreshold activation somewhere like here. And then it builds a memory trace that facilitates the recreation of the same peak. While in Hebbian learning, you would only strengthen the connection, the where this activation came from. So if it comes from the same input, then it would be strengthened. You see that what I just mentioned, that a neuron has many synapses, and only a very small subset of them is capable of creating a firing. Then Hebbian learning is a much more specific thing, right? You're localizing among all the possible inputs, ones that you're now more sensitive to, but you're not going to be more sensitive to the others. While the memory trace would just generally make it much easier to fire that neuron, and you can bring about that firing in from any of its combinations of inputs. So it's a much cruder method, but that has some strength. And the strength in DFT is that you can recreate activation patterns autonomously. You can, once you have laid down a memory trace, you can bring the memory trace into an activation peak through detection stability. So you can create macroscopic activation patterns in the brain without any specific information about where, which unit to activate. Right? This is the case where you really leverage this dominant recurrent connectivity in the neural fields. Good. Then I had this lecture on the neural grounding, which was population code. So that introduced those of you who are not familiar with neuroscience with this idea of tuning in the motor. I had a visual example, the motor example. In the motor example, tuning consists of neurons firing under particular conditions, for instance, particular movement directions here in the bottom, and all these little markers, which are spikes, would be more densely activated here for these directions than for those directions, also modulated in time. So really related to preparing the movement, actually most active before the monkey lifts the hand off the center button. And taking the tuning curves of these neurons to the parameter varied, the movement direction, and multiplying them always with the current firing rate is some kind of, the tuning curves are like basis functions, and this would be like a representation of the population activation based on these basis functions. And the main point about that was that in this way of linking fields to individual neurons, you see that neurons are actually smeared out across the field. They contribute the whole tuning curve. And that's some kind of like a dual space operation that shows that the neural fields are a little bit more abstract than just thinking about them on the cortical surface. And there's a whole interesting direction of research that we're doing about that. I don't want to go deeper into that. This is a very nice example from Paul Zizek's data in John Kalaska's lab almost 20 years ago, where they did the same experiment, but with locations in reaching space that are further and 80 degrees apart. So you can really see that there are first active, some firing for both options. And when you give the unique cue, only one of those survives, the other one is actually inhibited. You really see the inhibition here from the selection. And then when the movement is done, the peak grows further. Actually then decays, but it's also interesting, so not really accounted for by our model so far, even though in other areas we're thinking about things like that. It's called active transient, where you generate a single, it's sort of like a spike, create a single pulse of activity. Good. Yeah, so that's a single field, discrete neurodynamics. That's what you covered in your essay. And so I'm assuming that you will be quite familiar with that, and that will be something you really, I think, really might really now understand well. When we go to these higher cognitive things, I'm going to be much more selective. And so now I'm presenting just more selective ideas in there. And I'm not expecting you to have that same depth of understanding, even though it will, the things I'll mention now are the ones that you might want to be able to understand somewhat clearly. So the notion as we went higher was first this idea of a joint representation, that is saying I could have neurons that are tuned to two very different things, like being tuned to spatial location and color, so that a visual scene like that along one spatial dimension with this color here would generate localized input in 2D. This green would be here, this location, this green, this blue, this location, and that blue. And so you could say that these are bound or anatomically bound by having different neurons for every combination of those two ideas. And so that's a very general idea that has been used in cognitive neurophysiology. Almost all neurons in the auditory, visual, and actually also so much of sensory system have a spatial dimension, where you're on the skin, where you're on the cochlea, where you're on the retina. And they have a feature dimension, that is, they are reacting only to certain colors, certain orientations, even for the skin, certain directions of force, cochlea, pitch, and so on. So they're combining these two kinds of information. And that fact that you're having these different kinds of dimensions enables a couple of operations. If you have this bound representation, you can extract the individual components by just projecting out space, or projecting out color. You can also combine, assemble representations, but if you know color and space, you can sort of combine it to create a bound object. And that's where you have a binding problem. That is, if you blindly do that, then you would get misbindings or illusory conjunctions, where a blue thing here on the right could also induce a blue here on the left, and a green one here on the left could also induce a green on the right, because you don't know, is the blue one the one on the left or on the right? So you have to do this one object at a time, and that's one origin of the sequentiality bottleneck in all across the nervous system. It's kind of interesting idea. The special case of visual search is where you combine these two things. That is, you have a 2D representation, you want to select within the 2D representation one of those based on a cue, for instance, knowing the color. And you do that by now making a selection among these, biasing the selection by having a boost along the spatial dimension, which you don't know, localized along the feature dimension. So for instance, this one would win the competition because it has that boost, and therefore then you can read out its location. That's visual search, and we had much more elaborate models of that. And visual search stands for the general idea of search. If you try to select an idea, for instance, when you give a talk, you could say, well, you're providing some cues as to what kind of idea you want, maybe with some feature values, and that means now a population of neurons that is compatible with that is a little bit more activated than anything else, and now you just boost the population, and one of those biased, boosted ideas has a chance to come forward. So in a talk like this, they would use all these scientific ideas, and maybe it was much less likely that, I don't know, the name of my girlfriend comes up or something, right? So you could see that it's a very general idea of how you could operate, do search-like processes in neural substrate. Coordinate transforms was another application, and this is a bit more complicated. I'm not going to ask you to understand it very deeply. It is based on a joint representation of something you want to transform, like your retinal field, with a parameter that determines what transform you want to make. For instance, if you want to transform the retinal field into a body-centered field, you might need to know where your retina is relative to your body. Could be your gaze direction. And that joint representation then allows you to extract that transforms dimension. That's also a very general idea. Coordinate transforms are trivial if you write them down as equations, right? But in the brain, you can't really write down equations, right? You have to have some neural machinery that does that. And that's this idea that's called sometimes gain field. So this is something I don't really require you to understand, but if you do, it's like a bonus. You can do a lot of things with that. And the last notion in this binding lecture was this binding through space. It's also a more advanced kind of notion. So there will be the idea that you don't have to combine anatomically all possible feature dimensions with each other. A very high dimensional space that could require a lot of neurons. You can instead just have a lot of individual representations, for instance, color over space and then shape over space, as long as they share one dimension. So in the classical argument, it would be the retinal visual space that would be very often the shared dimension. And when you do that, then you can search for something in one space. For instance, here for color, color search by a boost here along space at localizing color. And by projecting through the shared dimension space, you can find the matching object like this one in another representation and then read out its feature value here, shape. Like you can say the green letter is the letter S. Yeah, that was this idea of space. And in our work was generalizing this idea that it's not always just space. There could be other dimensions, and I didn't really talk about that. Daniel Sabinas, whom you of course know, did in his doctoral thesis actually a generalization where he replaces the space notion with something we call an index notion, which is something like the temporal order in which you attend to objects. Like in speech, you would say things come in a particular order, and by saying the third thing that came in and everything that's connected to that third thing, you can sort of look up different aspects of that third thing, like the third word, let's say, different piece of information associated with that, all through the fact that it came in third. That will be a binding dimension. That's very advanced, so I'm requiring you to understand that fully. Yeah, and then the two last lectures, the most advanced, were on grounding concepts. This is exactly the sort of thing where we're not trying to do something high level. If I say relational to the left of, right? Spatial relations, I argued that is something really deep. People take a long time to learn what that means, left, right, and above. Some people never manage. And they can still apply to their sensory motor stuff, because if you just say the red to the left of green, you can sort of find out it is this one. Here, actually, this is a little bit trivial because if there's just one red, so you could just say red and you need to know that it's to the left of the green. But there could be, of course, cases. I'll show you one in a moment where there are multiple objects, and this would be uniquely picking out one by referring to a reference object, the green target on the right. And to perceptually ground that would mean that you link the sensory motor to this high-level concept, right? That's why we're choosing this entry into higher cognition, and we're not the only ones, of course. That is part of the embodiment tradition in cognitive linguistics. And so this was this complex architecture, and all you need to know about it is that it combines concepts, methods or scientific concepts that you're familiar with here, the visual search machine, which gets the visual input as these dimensions. You can search by putting in slices here. And then the coordinate transform machines here, where you represent a target object relative to a reference object. These sort of kernels for the spatial concepts versus kernels for like color concepts, and kernel for color concepts would be just some localized pattern that a yellow node activates stuff here around yellow, and I don't know, a red node activates something around red, and so on. Yeah, and then that together somehow did that binding. And again, it's not that grounding, and it's not something I will ask you in detail. We had some sequence generation here. For instance, this is a architecture how the reference object will be looked at first, and only when it's done, this is the condition of satisfaction, would it then actually allow the inhibit here, this precondition node that had previously inhibited the target one. So this looks first for a reference object. Only when that's done, it looks for a target object. So you recognize this from the last lecture, intentional node, condition of satisfaction node. This was part of this chaining idea that there would be a fixed order where you go from here to there, from reference to target. So that's how the autonomy came about, which I didn't actually explain in this grounding lecture, but I explained that in the last lecture. And this was sort of the triumph that you could then do hypothesis testing, in this scene where there are now multiple red objects, and only one of which is to the left of the green. So it's this one here. And where the system might actually select this one here on the left because it's larger, and then is able to autonomously reject that hypothesis based on a condition of dissatisfaction. I just reminded you of the condition of satisfaction. I didn't really explain the dissatisfaction system so well, but based on that, it could autonomously generate a new selection that then leads to it recognizing the correct target, which would be here, this one. Now, that is something that we consider to be higher cognition, even though it's still very much connected to the sensory surface. Yeah, and then the last lecture last week was about sequence generation, and pretty much all the material was in here. We argued that that's a very general property. And again, this is maybe an idea that you might be able to understand, that the notion is that an intentional state, the state that is aimed at achieving something, would sort of set up a system that will signal what we call the condition of satisfaction. That is, that intentional state is now done, is finished. So this prediction would set that up, and then some information from the sensory motor world or from some internal coupling would detect that that is actually the case by having overlapping input, and that goes through detection instability, which would then inhibit this field, which would go through reverse detection instability, and then that would reduce the input to that, and this would go through a reverse detection instability, and then the system is reset, and you can do something new using the surge-like idea that it would activate whatever is next most activated, right? Very simple idea of how sequences are generated, but quite original. I mean, this is really not something that is routinely solved in neural networks. Most neural networks that you find in machine learning are actually sequentially organized by some algorithm that just uses them, queries them, looks for the maximum, decides what next to do. And there are some models in cognitive science that look like they do something sequential, but they actually are just running transient. So one triggers the next and so on. It's just a big transient. And so if you take a little longer somewhere or something goes a little faster, then it gets totally out of sync and the system fails. So these are not really, they're sort of toy models. They don't really work when you do them connected to real sensors and real motor systems. So this is quite an original contribution of our way of thinking. So yeah, I showed you this robotic demo in which the system gets a serial order and then has to act out that serial order autonomously. And here it really goes from one to the next on its own. There's nothing external that tells the system to do that in a particular way. It's all just one state detecting that it's done, and then the next state and so on. Good. So this is the summary of the summary. So the key idea of DFT, what is the key idea? So the neurodynamics at the population level are about, that we capture those by these equations, the neurodynamic equations, population level description, and that these patterns are generated largely by recurrent connectivity, not by input. Such states must be stable, that if they're not stable, then competing inputs will just not create a consistent activity over time, and that will not really have behaviorally consistent properties. So to be functional, they have to be stable. These localist representations in low-dimensional spaces make such stability possible. It's not easy to think of other patterns that could make such patterns stable. So we're actually thinking it might be the only kind, but it's up to debate. And then instabilities create this capacity to do all kinds of things with that, including sequential processing, which is the most important one. So there will be, population level. I didn't write down the dynamics, but that's implied here. Recurrent connectivity, stability, low-dimensional localist representations, sequence, instabilities leading to all kinds of cognitive functions. 5 ideas. Study that slide. Okay, so I'll close by reminding you, I showed those slides in the introduction, and I said you learn academic skills, to read and understand scientific texts. I hope you did that a little bit. You read those chapters, for instance. Didn't do a lot of, I think I asked you to read one paper only. And then you did write technical texts, including illustrations and math concepts, and the essay was the high point of that, and some of the exercises earlier also had that. Mathematical skills, you have some conceptual understanding of dynamical systems now, I hope, and thus when you see a differential equation, you can make sense of it and maybe illustrate it, plot it in the usual form, maybe do mental simulation in the sense you understand, it goes to the attractor and have some kind of idea of how selection works and so on. So that's understanding properties of the solution just from looking at the equation rather than analytically solving it. And we had a little bit of opportunity in these interactive simulation exercises to see how numerical simulations can be used when you have such equations. Maybe from that you got a sense that it's much less powerful than mental simulation or analytical thought, which would be the more precise version of that. That is, once you do numerical simulations, you have to do essentially experiments, do procedures, hypothesis, and then try it and observe and so on. It's much more complex, much less generalizable. So you can see the methodological constraints in mathematical modeling of that nature. So I'm hope that has really happened. And the last most general skill, this interdisciplinary skill. So I'm sure that for everyone here, there were concepts from different disciplines. The computer science or physics folks certainly didn't know about some of those cognitive things like memory or binding or grounding and things like that. And then conversely, of course, cognitive scientists, for instance, really had maybe not heard so much about neurophysics or these kind of equations and stability and so on. So that's an important skill because pretty much all intellectual work, including most professional work, is in contexts like that, where, let's say, an accountant and a marketing folk and a engineer and I don't know, some kind of logistics person, they all interact. And that means you always have to handle stuff that you don't fully understand. And that requires you to know that you don't understand it, and then to know how to find out about it and who to talk to and what to do about it. And that aspect, I call that metacognition. It's actually generally called metacognition, to know what you understand, what not. That's a very important skill for interdisciplinary work, but actually also just intellectual work in very general terms. And this is actually really directly relevant to the exam, because there is nothing worse you can do in an exam than say something that you don't even know what it means, just because you think, that's the kind of thing that the teacher likes to hear. He always says that, so I say something like that, but I don't know what it means. I find out very quickly, and that's the worst sin. So if you don't know, just say, I don't know. Or you could even say, this is the sort of thing that you say, but I don't fully understand it. That's good, because at least you know that you don't understand it. That is knowledge as well. That's good knowledge, very important knowledge. Hopefully there is something that you actually know, and it's not, if you, of course, only say the only thing is I know that I don't know anything, a la Socrates or Nietzsche, then that's maybe not yet the full cigar, but still very important to have metacognition. Good. So